In this lecture, I am going to present how to determine the redundant force of the portal frame using flexibility matrix method. As we know from the definition of flexibility, flexibility of a structure is defined as the displacement caused by a unit force. Let us take a one-dimensional spring. One end of the spring is fixed and other end of the spring is free. If you will apply a force P1 at the free end, so what will happen? The flexibility of a spring is defined as the displacement delta 11 at the coordinate 1 due to unit force at the coordinate 1. So if you will apply a unit force at the coordinate 1, so due to that unit force, so what is the displacement takes place? That is called the flexibility at the coordinate 1, delta 11. Then what is flexibility matrix method? The flexibility matrix method of analysis is basically a consistent displacement method cast in matrix form. This method can be used for the analysis of statically determinate as well as indeterminate structures. In this method, the basic unknowns are redundant forces. Hence, the analyst has to first identify the basic determinate structure and thereby identify the redundant forces. The number of redundant forces is equal to the degree of static indeterminacy. So, in this method, what you have to do? First, you have to find out the degree of static indeterminacy. Then, the number of degree of static indeterminacy is equal to the number of redundant forces you have to choose. Then, the displacement in the basic determinate structure due to a given loading and the redundant forces are found and the consistency conditions are found. Then what you have to do? You have to find out the displacement in the basic determinate structure due to given loading and also due to the redundant forces. The resulting simultaneous equations are solved to get the redundant forces. You will get the number of simultaneous equations. Then after solving that number of simultaneous equations, you will get the redundant forces. This method is also known as force method or compatibility method. This method is known as force method because the compatibility equations are derived by the superposition of two systems of forces. One applied loads and other the redundants. Another reason of this method, the forces are treated as unknowns. That's why this method is called the force method. This method is also known as flexibility method because the flexibility matrix has to be developed to establish the compatibility of displacements. The method is also known as the flexibility method because the flexibility matrix has to be developed to establish the compatibility of displacements. Also, this method is called the compatibility method as the condition of compatibility of displacement is utilized in this method. So, it is also known as compatibility method. These are the steps used to solve any statically indeterminate structure using flexibility matrix method. First, you have to determine the degree of static indeterminacy of a structure. Then you have to choose the redundant force according to the degree of static indeterminacy because you have to take the number of redundant forces is equal to the number of degree of static indeterminacy. If there are n redundant forces, then you have to choose n coordinates. Then you have to choose n coordinates. So, assign the coordinates 1, 2, 3 and to the redundancy. If there are 3 degree of static indeterminacy, then you have to choose 3 redundants. Then you have to assign the 3 coordinates 1, 2, 3 to the redundant direction. Then remove all the redundant to obtain the release structure. Then you have to remove all the redundant to obtain the release structure. Then determine the displacement in coordinate direction due to the given loading condition in the basic determinate and release structure. Then you have to find out the displacement in coordinate direction due to the given loading. Then you have to find out the displacement at the coordinates due to the redundant force delta r. Then compute the net displacement at coordinates. Delta is equal to delta L plus delta r. Delta is equal to delta L plus del into P. Apply the condition of compatibility of displacement to compute the redundant. Then the redundant force is equal to del inverse delta minus delta L. This is the net displacement and this is the displacement due to the external loading. This is the flexibility matrix. This is inverse of the flexibility matrix. Knowing the redundant, compute the internal member forces by using the equation of states. After getting the redundant force, then you can find out the internal member forces by using the equation of states. And these points you have to remember for assembling deflection in release structure due to the external loading, and also assemble the flexibility matrix. Use these methods. So you can use the conjugate beam method or unit load method to find out the deflection due to the external loading and deflection due to the redundant forces. So this method you have to know to find out the deflection by taking the loads or by taking the redundant forces. Any one method you can use for the analysis of any structure. Then coming to one problem, here I am going to solve one problem. Analyze the portal frame ABCD in figure by flexibility matrix method. EI is constant throughout. This is the portal frame ABCD. The height of AB is given 4 meter and BC length is given 4 meter and CD height is given 2 meter, and the EI is constant throughout, and on span BC there is having the UDL 30 kilonewton by meter, and on the span AB at point B there is having a concentrated load, horizontal load 50 kilonewton. The end A and D is fixed. You have to solve this question by flexibility matrix method. So what you have to do first? So first you have to find out the degree of static indeterminacy. Here you see the support A is fixed and support D is fixed. So at support A there are 3 reaction components and at support D there are 3 reaction components. So how many total reaction components? 6. Then how many static equilibrium equations available? 3. So what is the degree of static indeterminacy? The degree of static indeterminacy is equal to R minus 3. R is equal to 6 minus 3. This is equal to 3. So the degree of static indeterminacy of a structure is equal to 3. So from the definition, from the procedure, you know the degree of static indeterminacy is equal to the number of redundant forces. So here you have to choose 3 redundant forces. Here you have to choose 3 redundant forces. That is, you have to choose the redundant forces at the support D. One redundant force is the vertical direction at D, and the second redundant force is the horizontal direction at D, and the third redundant force is the moment at the support D. HD, VD and MD. HD the horizontal force at D, VD the vertical force at D, and MD the bending moment at D. So this is the redundant force P. P is equal to HD, VD, MD. HD, VD and MD. These 3 are the redundant force. Then what you have to do? So you have to assign the coordinates along these 3 redundant force. Hence coordinates 1, 2, 3, 1, 2 and 3 selected are as shown in figure 2. So this is the this is horizontal force HD, this is the vertical force or vertical direction VD, and this is the moment at D, this is MD. So this is the first coordinate and this is the second coordinate, the vertical direction, and this is the third coordinate, the moment at D. SD one coordinate, and BD the second, and the MD this is the third coordinate. This is the three coordinate direction. SN these three coordinate direction. The basic determinate structure is a cantilever frame. The basic determinate structure is a cantilever frame. The required deflection may be calculated from the unit load method. So here we will apply the unit load method to find out the deflection at the coordinate 1, 2, 3. The expression for moment due to load M1 and due to the unit load in coordinate direction M1, M2, M3 are shown in table 1. So what you have to do? So you have to find out the moment due to the external load. So what is the load is given on the portal frame. So due to that load, you have to find out what is the moment on span CD, then CB, then AB. Then you can find out what is the displacement along one direction, along two direction, and along three direction. You have to find out the displacement. Then you have to find out the moment on span CD, CB, and BA by applying the unit load along the coordinate direction 1, then along the coordinate direction 2, then along the coordinate direction 3. First you have to find out the moment on span CD, then CB, then AB. Then after getting the moment, then you can find out the flexibility matrix. Then you can find out the flexibility matrix. So what you have to do? So first you have to find out by considering the external loading. So you have to find out the moment in each span. Then by applying the unit force in coordinate direction 1, you have to find out the moment in each span. Then by applying the unit force in coordinate direction 2, you have to find out the moment in each span. Then by applying the unit moment in coordinate direction 3, you have to find out the moment in each span, CD, CB, and AB. So due to external loading, take the moment capital M1, and due to unit loads in coordinate direction, take M1, M2, M3. You take M1, M2, and M3. So first moment due to external loading. So this is the external loading present, and you have to remove all the other redundant forces. You have to remove these forces, ST, and this is these redundants you have to remove. Only you have to consider the external loading, and due to that external loading, you have to find out what is the moment in span CD, then in span BC, then in span AB. Let us take a section at a distance x from the D. So what is the moment here? Because here on this span CD there is no load, so the moment here is equal to 0. Then take on the span BC one section at a distance x from the support C. Then what is the moment here? What is the moment on this section? So because this is the load is present here, 30 kilonewton by meter, and what is the total load? 30 into x. And what is the moment? So the central distance into this section, this is x by 2. So 30 into x by 2, 30 x square by 2, that is equal to 15 x square. Here you see in a tabular form, here this is 15 x square. For DC 0 and for CB 15 x square. Then take another section on the span AB at a distance x from the support B, and you have to find out what is the moment here. You have to find out what is the moment here. So what is the moment here? So because this is 30 kilonewton by meter, and this is the length is 4 meter, 30 into 4, and this is the what is the central distance, what is the moment of this total load about this point? 30 into 4 into 2, 30 into 4 into 2, due to this UTL, 30 into 4 into 2, this is equal to 240 kilonewton meter, and due to this load, what is the moment here? 50 into x, 50x plus 30 into 4 into 2, this one 50x plus 240 for BA. Similarly, find out by considering the unit force in coordinate direction. Then you find out the unit force in coordinate direction here. and here so this external force you have to remove. Only have to consider the unit force. Only have to take the unit force here and remove all the external forces. Remove all the external forces. Remove all the external forces. Then find out what is the moment in span CD and BC and AB. What is the moment here? Take a section at a distance x from the point D. Then what is the moment due to this unit force? 1 into x. This is anti-clockwise direction. So take this is minus x. This is minus x in span CD. Then take a section at a distance x from the point C. So what is the moment here? What is the moment here? So this is 1 into 2 perpendicular distance. This is also minus anti-clockwise. Minus 1 into 2. This is minus 2. So here minus x and here the moment is minus 2. Similarly find out here what is the moment. So this is 1 and this total length is 2 and this is x. Minus 1 into 2 minus x. Minus 1 into 2 minus x. So this is equal to minus 2 plus x. Minus 2 plus x. So here the moment is minus 2 plus x. This is for CD, this is the moment minus x. For CB, this is minus 2 and for BA minus 2 plus x. This is due to the unit horizontal force. Then apply unit vertical force. Unit vertical force at D and remove all the external loading. Remove all the external loading. Remove all the external loading. Only you take the unit vertical force. Only unit vertical force. Due to this unit vertical force, find out what is the moment here and what is the moment here and what is the moment here. So take a section at a distance x from the T. So what is the moment here? Because this unit force is passing through this point, so the moment here is equal to 0. Due to this unit force, vertical force, the moment here is 0. Then take a section at a distance x from the point C. So what is the moment here? This is 1 into x. So here the moment is this is anti-clockwise, minus 1 into x. Then what is the moment here? Take a section at a distance x from the point B. So what is the moment here? This is minus 1 into 4. This is anti-clockwise, minus 1 into the perpendicular distance. So here this is minus 4 and here minus x and here 0. Just to put here 0 and here minus x and here minus 4. So this is clear. Then what you have to do, apply unit moment at a point D and find out what is the moment here. Apply unit moment at a point D and find out what is the moment in span CD, BC and AB and remove all the external forces. Remove all the external forces. So what is the force is given, that remove. Only you take the unit moment. Only you take the unit moment at D. Remove all the external force. Only you take the unit moment at D, and due to this moment find out what is the moment in span CD and in BC and in AB. So let us take a section at a distance x from the point D. So what is the moment here? If the moment here is m 1 kilonewton meter, then what is the moment here also? 1 kilonewton meter. Similarly take a section at a distance x from the point C. So what is the moment here? If here the moment is 1 kilonewton meter, here also that is 1 kilonewton meter. Similarly, take a section at a distance x from B. So what is the moment here? Here also the moment is 1 kilonewton meter. So in span CD, this is 1 kilonewton meter at any section, and in span BC, the moment is 1 kilonewton meter, and in span AB, the moment is 1 kilonewton meter. Just to write here in tabular form. So these are the moment due to given loading and unit loads. This is the flexural rigidity EI for DC, CB and BA. This is DC, then this is CB, then this is BA. Then the origin you take for DC D, and for BC C, and for AB B. This is the origin D, C, B. Then what is the limit? So here the limit of integration is 0 to 2. For DC the integration of limit is 0 to 2, and for BC the integration limit is 0 to 4, and for AB the integration limit is from 0 to 4. 0 to 2, 0 to 4 and 0 to 4, and these are the moment. So this moment is due to the external loading in DC, CB and BA. Similarly, this moment is due to the unit horizontal force, and this moment is due to the unit vertical force, and this moment is due to the unit moment at D. These are the moments that is present in a tabular form. Then using the unit load method, find out the displacement due to the external loading first. So displacement due to given loading in the release structure. First you find out what is the displacement in coordinate direction 1, 2, 3 due to the given loading. So this is the formula you have to take, delta 1L. This is the displacement in coordinate direction 1 due to the external loading, delta 1L. Similarly, delta 2L is the displacement in coordinate direction 2 due to the external loading, and delta 3L is the displacement in coordinate direction 3 due to the external loading. So delta 1L, the formula is capital M small m1 by EI into dx integration. This is the formula to find out the displacement in coordinate direction 1 due to the external loading, capital M small m1 by EI into dx, and the displacement in coordinate 2 due to the external loading, that you can find out. This is the capital M small m2 by EI into dx. This is the formula. Similarly, the displacement in coordinate 3 due to the external loading, that you can find out capital M small m3 by EI into dx. This is the formula to get the displacement due to the external loading. So you know here the M, capital M and small m1. You know here capital M, this is capital M and this is small m1. This is due to the external loading. This is the moment due to the external loading. This is the moment M due to external loading. This is the moment due to the unit horizontal force. M, capital M small m1 by EI into dx. So here for DC, so this is 0, and for CB 15x square minus 2, and for BA 50x plus 240 into minus 2 plus x, and here the integration limit for CB this is 0 to 4, and for BA 0 to 4. For CB this is 0 to 4, 15x square minus 2 by EI into dx, and for BA 0 to 4, 50x plus 240, 50x plus 240 minus 2 plus x. This is capital M and this is small m1, capital M small m1. Then take the integration here. So after taking the integration, so you get delta 1L is equal to minus 373.33 by EI. Similarly, find out delta 2L, integration of capital M small m2 by EI into dx. Here also you take, this is capital M and this is small m2. Here this is 0, 0, for DC 0, and for CB 15x square into minus x, 15x square minus x, that is minus 15x cube by EI into dx, integration 0 to 4. Then for BA this is 15x plus 240 into minus 4, 15x plus 240 into minus 4 by EI into dx, and integration 0 to 4. Then after taking the integration of this expression, you will get delta 2L is equal to minus 6400 by EI. Similarly, find out delta 3L. delta 3L is equal to integration capital M small m3 by EI into dx. Here also you have to put that capital M and small m3 value, capital M and this is small m3, for DC 0 and for CB 15x square into 1, 15x square into 1, 15x square by EI into dx 0 to 4 integration. Similarly, this is 15x plus 240 into 1. (15x plus 240 by EI into dx and 0 to 4). Then after simplification of this expression, you will get delta 3L is equal to 1680 by EI. So this is the displacement due to the external loading at the coordinate 1, 2 and 3. Then find out the displacement due to the redundant force. That is the flexibility matrix. You find out the flexibility matrix. So the flexibility matrix that you can find out, first you have to find out the displacement by applying the unit horizontal force at the coordinate 1. By applying unit horizontal force at coordinate 1, so find out what is the displacement, delta 11. Delta 11, I mean that is the displacement at the coordinate 1 due to unit horizontal force at the coordinate 1. Delta 11 is equal to integration of m1 square by EI into dx. You know what is the m1? You know the value of m1. m1 is your for DC minus x, for CB minus 2 and for BA minus 2 plus x. So here the integration limit is 0 to 2 and here the integration limit 0 to 4 and here the integration limit 0 to 4. Take here 0 to 2 x square by EI dx plus 0 to 4, this is 4 by EI into dx, and then plus 0 to 4 minus 2 plus x whole square by EI into dx. So this is the delta 11. Then after simplification you get delta 11 is equal to 24 by EI. Then find out delta 21 is equal to delta 12 is equal to integration of m1 m2 by EI into dx. And you know what is m1 and what is m2. So you put here delta 21 and delta 12. Delta 21 is equal to delta 12 is equal to 0 to 4 2x by EI into dx plus 0 to 4 minus 2 plus x minus 4 by EI into dx. Then after simplification of this expression, delta 21 is equal to delta 12 is equal to 16 by EI. Then find out delta 31 is equal to delta 13 is equal to integration of m1 m3 by EI into dx. And you know the value of m1 and m3. Then after putting m1 and m3, delta 31 is equal to delta 13 is equal to 0 to integration minus x by EI into dx plus integration 0 to 4 minus 2 by EI into dx plus integration 0 to 4 x minus 2 by EI into dx. Then after simplification of this expression, delta 31 is equal to delta 13 is equal to minus 10 by EI. Then find out delta 22. Delta 22 is equal to integration of m2 square by EI into dx. This is the formula. So here you know m2 value for m2. This is m2 for DC. This is 0, and for CB this is minus x, and for BA this is minus 4. And integration limit for CB 0 to 4, and for BA this is 0 to 4. Just to put this value here, m2 square by EI into dx, 0 to 4 x square by EI dx plus 0 to 4 16 by EI into dx. Then after simplification you get delta 22 is equal to 85.33 by EI. Then similarly find out delta 32 is equal to delta 23. So this delta 32 delta 23, this is the formula, integration of m2 m3 by ei into dx. This is the formula by unit load method. Delta 32 is equal to delta 23 is equal to, so here you have to put the value of m2 and m3. Then after putting this one, 0 to 4 minus x by ei dx plus 0 to 4 minus 4 by ei dx. Then after simplification, this is the value. Delta 32 is equal to delta 23 is equal to minus 24 by ei. This is the value after simplification. Then find out delta 33. Delta 33 is equal to integration of m3 square by ei into dx. You know m3 for m3 for DC, CB and BA 1 1 1. So just you put this one. One by ei into dx, integration 0 to 2 plus 0 to 4 1 by ei into dx plus 0 to 4 1 by ei into dx. Then after simplification of this expression, you will get delta 33 is equal to 10 by ei. So these are the displacement due to the unit horizontal force at the coordinate 1 and the unit vertical force at the coordinate 2 and the unit moment at the coordinate 3. Then you know the compatibility equation, del P is equal to delta minus delta L, but del is the flexibility matrix. So here you got the flexibility matrix, here you got the value of the flexibility matrix. These are the coefficient of the flexibility matrix. These are the coefficient delta 1 1, this is delta, this is delta 1 1, then you got here delta 2 2, delta 3 2, delta 2 3, then delta 3 3, then you got, then after putting these values, delta 1 1, delta 1 2, delta 1 3, then delta 2 1, delta 2 2, delta 2 3, delta 3 1, delta 3 2, delta 3 3. Then after putting here, you will get here, this is the flexibility matrix, 3 into 3 matrix, and these are the redundant force P1, P2, P3. This you have to find out is equal to, there is no displacement at the coordinate 1 2 3, so you have to take this is equal to 0 0 0. Then minus here, this is the displacement due to the external loading, minus 1 by ei. Here you got displacement due to external loading in coordinate direction 1 and in coordinate direction 2 and in coordinate direction 3. This is delta 1L, delta 2L and delta 3L. This is delta 1L, delta 2L and delta 3L. So just have to put here. Delta 1L, delta 2L, delta 3L. Then you have to find out the redundant force P1, P2, P3. So you take the inverse of this flexibility matrix. Take this side, this is 1 by ei, 1 by ei cancel, and you take this side, this is the inverse of this flexibility matrix, and this one the displacement due to the external loading. Then find out the inverse of the flexibility matrix. Find out the inverse of the flexibility matrix, then multiply with the this column matrix. Multiply with the column matrix, then we will get what is the force P1, P2 and P3. So this is the P1, P2, P3, and this is the inverse of the matrix. This is the inverse of the matrix, you know. Then this is the column matrix displacement due to the external loading. Then after multiplication of this one, then you will find out the P1, P2, P3 is equal to minus 53.33, P2 is 70.01 and P3 is minus 53.33. So the P1 is equal to the horizontal force at D, so this is equal to minus 53.33 kilonewton, and P2 is equal to the vertical force at D, this is 70.01 kilonewton, then P3 is equal to the moment at D, this is minus 53.33 kilonewton meter. But here you got here the negative value. So before solving the question, you are taking the horizontal force is your right direction. So here you take, this is the horizontal force at D is your left direction, and the vertical direction at D, this is your positive. So this is the assumed direction is okay. So this is vertical direction, and the moment here you are getting minus 53.33 kilonewton meter. You are assuming this is clockwise direction, but here you have to take, this is anti-clockwise direction. Here you got the moment is your minus 53.33. So here you take, just to write here anti-clockwise direction and don't write here the minus. So 53.33 kilonewton meter anti-clockwise. So these are the redundant forces. So here you got using the flexibility matrix method. Then after knowing the redundant force, then you can find out the internal member forces. You can find out the moment, then you can draw the bending moment diagram by the equation of statics. Then you are clear. So how to solve the portal frame using the flexibility matrix method.